I wanted to start this video by looking at another example of a heteronuclear diatomic molecule. This time it's the cyanide anion, Cn-. We're going to take a look at the molecular orbital energy diagram. We're going to infer the bond order from the molecular orbitals and look at the Lewis structure and compare to the bond order implied by the Lewis structure, the number of lines linking the carbon and nitrogen atoms, and notice a couple of interesting things about this molecule. So the first thing I would point out about this molecular orbital scaffold is this actually looks a little bit different from the NO diagram that we looked at previously, in that the sigma 2p orbital is higher in energy than the pi 2p orbitals. This indicates that sp mixing is occurring in this molecule, and this is because carbon and nitrogen are not very electronegative, so we get, for example, relatively close energy between the sigma 2p and sigma star 2s orbitals. This causes them to interact, to mix, to create a new bonding and anti-bonding combination, if you will, or constructive and destructive combination, we might say more generally. And this pushes down the sigma star energy and up the sigma 2p energy to push this above the pi 2p. This would be difficult to predict in general. I mean, we might infer it or guess it based on the corresponding diatomics, C2 and N2, but this would be a case where I personally would give you this molecular orbital energy diagram and the energetic ordering of the sigma and pi orbitals, just to take any educated guessing with sp mixing off the table. All right, let's add electrons to this MO diagram and infer the bond order of the cyanide anion. All right, so we start with the Lewis structure for cyanide. Carbon has 4 valence electrons when neutral, nitrogen has 5. We have an extra electron in this molecule because it's an anion, so there are 10 valence electrons total. And if you go through the motions of drawing the Lewis structure, you'd find that to satisfy the octet rule, we need a triple bond between carbon and nitrogen and 1 lone pair each on carbon and nitrogen, with the formal negative charge on carbon, at least in the resonance structure I've drawn here. All right, let's start with the atomic electrons. Now, I'll draw your attention to the way I've labeled the atoms on the outside of the diagram with C- and neutral nitrogen. I'm going to throw an extra electron into the carbon valence atomic orbitals because I've indicated the negative charge here. The MO diagram, the molecular orbital occupancies, are going to come out the same whether I put the extra electron on carbon or nitrogen, but I did this because this is consistent with my Lewis structure with negative formal charge on the carbon atom. It's all going to come out in the wash once we start putting those electrons in the molecular orbitals. Now, to fill the molecular orbitals, we know how to do this using the Aufbau principle and Hund's rule. We start at the bottom, sigma 2s bonding pair, sigma star 2s anti-bonding pair, 4 pi 2p electrons, 2 sigma 2p electrons, and I believe we have accounted for all 10 valence electrons now at this point. All right, great. So we can notice a few things from this. We've got an overall bond order involving 8 bonding electrons and 2 anti-bonding electrons. That's going to correspond to a bond order of 3, and that's exactly what we observe in the Lewis structure. Yet another instance of the best Lewis structure agreeing with the bond order implied by molecular orbital theory. I would also draw your attention to, we have essentially 2 pi bonds and 1 sigma bond derived from the p orbitals, and this would be sort of what we would expect based on prior discussions of valence bond theory. So the MO description and the valence bond description here actually agree pretty well. And although we won't look at the shapes in detail, this is a good opportunity to pause and think about what you'd expect the shapes of these orbitals to look like. Would you expect the sigma 2s orbital to be skewed toward carbon or nitrogen? Think about things like electronegativity and do the same sort of exercise for the anti-bonding orbital, the sigma star and pi star and sigma star 2p orbitals as well. We've talked a lot so far about how molecular orbital theory can be used to visualize and describe molecular electrons, allowing us to infer things like bond order and numbers of bonding and anti-bonding electrons. But there are real implications of molecular orbital theory, and one of those real implications has to do with magnetic properties. Molecules containing unpaired electrons are what we call paramagnetic, and paramagnetic molecules are strongly attracted to a magnetic field. And we can actually Notice this. So what you see in the image on this slide, for example, is liquid oxygen. So oxygen that has been condensed to a liquid at very, very low temperatures. And if you pour that liquid oxygen between the poles of a magnet, you'll notice the oxygen gets trapped between the two poles of the magnet, and this is because those O2 molecules are actually attracted to the magnetic field. So the magnetic field holds them in place. It's remarkable. It's a remarkable effect. Most normal molecules, I'll say, do not display this effect, and molecules that essentially don't interact with magnetic fields are called diamagnetic. This is another term that we'll want to commit to memory and get familiar with, because we'll often be asked to evaluate whether a given molecule is paramagnetic, or atom or ion is paramagnetic or diamagnetic. So diamagnetic molecules, I'm going to say negligibly weak interaction with the magnetic field. Now, what is it about O2 that makes it paramagnetic? Well, it's the unpaired electrons, and that's why I like the para in paramagnetic. You have to, I guess, kind of add the but unpaired electrons are associated with paramagnetism, and we can see those unpaired electrons directly in the molecular orbital energy diagram for O2. So here it is. I won't go through it again. We've seen this diagram before, and the really key thing to notice now from the perspective of magnetic properties is these two unpaired electrons in the pi star 2p orbital. These give rise to the paramagnetism of dioxygen. Most molecules lack unpaired electrons. All of their electrons are paired up, so in the molecular orbital energy diagram, you'll see all of the electrons, every up electron has a down electron partner in every orbital, and every orbital is either completely filled or completely empty, either two electrons occupying it or none. And in those cases, we have a diamagnetic situation. Now, this one's a little easier to commit to memory. Di meaning two, meaning a pair. All electrons are paired in a diamagnetic molecule is how I go about remembering this. O2 is by no means the only molecule that displays magnetic properties like this, and actually in chemical principles too, we'll encounter transition metal cations that also have unpaired electrons that exhibit paramagnetism even when they're in complexes with molecules that have all paired electrons. This is a measurable effect, in fact. And so molecular orbital theory really helps us see how these magnetic properties arise in terms of why the molecule has unpaired electrons. Filling up the molecular orbitals in accordance with Hund's rule leads to electrons avoiding pairing in the ground state of the molecule. This slide simply summarizes the bonding and geometric theories we've covered so far in dealing with molecular structure, essentially our theoretical toolbox for understanding molecular structure. We started with Lewis theory, where we're thinking of electrons as dots and lines on a piece of paper. Electrons are localized, right? They're either between two atoms or on one atom. And we can get an idea of how strong bonds are roughly, thinking about things like bond order. We can recognize bonding patterns, how atoms tend to group themselves, and things like the octet rule are our guiding light along those lines. But it's got some serious drawbacks in that we know from quantum mechanics, quantum chemistry, that electrons are delocalized, and Lewis theory has nothing to say about that, and for example breaks down in the face of molecules that exhibit electron delocalization. Vesper is a geometric theory that follows from the Lewis theory, where we can use the number of electron domains around the central atom to infer the geometry, the electron geometry, the molecular geometry, etc. But it gives no insight into how or why chemical bonds form, and there are exceptions to Vesper theory that arise. For example, because it follows from Lewis theory, it's hard to reconcile Vesper with resonance, for instance. Valence bond theory was our first description of the chemical bond in terms of orbital overlap. But valence bond theory, again, is sort of a fundamentally localized theory. It uses things like atomic orbitals overlapping on adjacent atoms. It uses hybrid orbitals, which, again, localized, right? We're only talking about a pair of electrons between two bonded atoms. It really can't handle electron delocalization, and it also doesn't explain things like paramagnetism, where the orbital occupancy, the occupancy of molecular orbitals that we see in MO theory, really matters. And then finally, molecular orbital theory, which is certainly our most detailed theory of molecular structure, gives insight into how bonds form through different types of orbital overlap, how those orbitals are occupied with electrons, building on what we already know from atomic orbital theory, and can help us explain things like paramagnetism, diamagnetism, and even the bond orders that we observe in Lewis theory. So we're building up in complexity as we go from Lewis theory to molecular orbital theory, but each of these theories has their uses. You know, it's really kind of counterproductive to view one as better, quote unquote, than the other. It's just that the complexity sort of goes up. And for example, in the case of valence bond theory and MO theory, there are ways to show that these are theoretically equivalent, in fact, that you actually can build delocalization into valence bond theory. Won't go into those details here, but I would just encourage you to think of these theories as models that you can use to answer particular questions, get at particular insights, and the best model to use often depends on the question you're asking.